Okay, welcome again. So to remind you, yesterday we started discussing triangle configurations and we quickly reviewed the circumcircle, circumcenter, and centroid, which is the center of mass, and also in the case of 4 points, and more generally. And we learned about orthocenter and orthic systems, and we learned about the 9-point circle of an orthic system. So today I want to continue with further information, okay, about triangle configurations, the continuation of the previous page. So I want to, okay, the next thing I want to tell you is Euler line. Have you heard of this? Uh, so what this is that H, G, and O are collinear in a triangle. So what is H, G, and O? Orthocenter. So this is in a triangle, okay? In any triangle. This is the centroid. And this is the center of the 9-point circle. Center of the 9-point circle of the triangle. So by which what we mean is this is just the center of mass of the triangle with its together with this orthocenter. The 9-point circle. And this is the circumcenter. So let's prove this. And then I will draw a picture of this. This is very nice, really. Well, first of all, what we know is G is A plus B plus C over 3, right? And N is the center of mass of this. So this is 3G plus H over 4. So 3 over 4 G plus 1 over 4 H. You see, sum of the coefficients is 1. So this is a meaningful equality. So this immediately shows that N is in fact situated between H and G with a precise ratio. N is here with the ratio 3x here and x here. Because the coefficient of G is 3 times more, the distance to G is 3 times closer. So the center of the 9-point circle is in fact between the orthocenter and the center of mass with this ratio. So so how about the circumcenter? How do we know where the circumcenter is on this line? It is also situated with a precise ratio, you will see. But let me first draw a picture, and from the picture we can see maybe more easily. So do you understand this part of the proof? Is this convincing?
Yeah, it's clear.
So let's okay, let's draw the 9-point circle, which is okay. Since I want to focus on the triangle itself, I don't want to draw these segments with clarity. I just want to. So when you focus on the triangle itself, somehow you know the segments AH, BH, and CH are less important than the side lengths. So it is more important to say that the midpoints uh, of the sides and feet of the altitudes. These 6 points are on a circle. Of course, this is together with the midpoints of AH, BH, and CH. So this is the 9-point circle. And center of the 9-point circle is here, which is the midpoint of these diameters. So this is the diameter, as you can see. Or maybe let me put it here more like, sorry. Yeah, indeed. This is a diameter, this is a diameter. So I'll show these diameters. So this is N. But let me not show the diameters to not complicate the picture. Okay, maybe I can show it like this. And where is G? G is here, which is on these medians. See, this is the midpoint. So for example, this is a median. This is a median. Actually, maybe we should draw a bigger picture and really show everything very explicitly. It would be much better, yeah, I guess. Show everything very explicitly. Anyway, so I will draw hopefully a very big triangle. Yeah, first I can. Okay, let's draw the altitudes. So let's give a color for everything. So these are the altitudes, okay? So these are the blue are the medians. So blue are the midpoints of the sides. Red are the feet of the altitudes. So let's draw these with green. So from the midpoint of this to this is a diameter of the 9-point circle. From the midpoint of this to this is a diameter of the midpoint 9-point circle. So this is N. Again, similarly, so this is N. This is H. This is N, and this is okay. We should have drawn this more carefully. I think I can do it now. This is G. You see, they are situated on a line like this. Each one of them, so H is the intersection concurrency point of the altitudes. G is the concurrency point of the medians, and N is the concurrency point of these diameters. It's the center of the 9-point circle, as you can see. And they are on a line with this precise ratio. And this can really be seen. There is a lot of Menelaus theorem you can do here. You can show that H and G are, I mean, once you draw this figure, so this by itself is a very short direct affine proof. This thing that we do here is a very short direct affine proof. But once you draw this configuration, if you want to find another proof, it's very easy to find with Menelaus theorem, because all the ratios here are clear. Right? The ratio here is, yeah, there is, 1/2. If you do it with the triangle, on the triangle B, this point and this point. If you do Menelaus theorem with H and G, you know Menelaus theorem, right? Do you know? Have you seen Menelaus theorem or not?
Actually, I have not read about.
What? You have not seen?
I have not seen it before.
Oh, okay, okay. So, okay, Menelaus theorem, since I thought Menelaus and Cheva theorems are more basic than these, I didn't discuss them, but okay, I will tell you about those later. It's in fact some theorems coming from these affine ideas, okay?
But actually, I know about Shifa's theorem.
Oh, okay. Menelaus and Shiva are basically twin theorems. They're brothers. So okay, uh, they're two sort of like different versions of similar things. They are both affine theorems. So coming from this kind of affine thoughts. Uh, so in Cheva's theorem, you have three lines that are concurrent, coming from the vertices of a triangle, right? You know this, right? There's a triangle and there are three lines coming from the vertices of the triangle that are concurrent. And you have something with the ratios on the sides. In Menelaus theorem, instead of three lines that are concurrent, you have 3 points that are collinear on the sides. Okay, on the sides of the triangle. So anyway, yeah. So you can prove that they are collinear like this. So how about O, the center? Circumcenter is here on the perpendicular bisector. Okay. So this O is in fact also on this line. So this is the Euler line, okay? Let me draw the Euler line for you. Let's prove this. Again, there are many ways to prove. Uh, but let's find a good argument to prove this. So one good way to prove it is this. So consider these green points and do homothety. You know the basic notion of homothety, right?
Yeah, we do.
Do homothety from H with ratio 2. What does this give you?
From H or from G, I think.
No, from H. Well, with the green points you can do from H. So there is also another homothety that we can do from G with the blue points. But so
Oh,
I will explain this to you in two different ways. So from H and from G. Uh, but let's just do this
okay.
from H. From H with ratio 2. The green points go to the vertices. Okay. This was the first thing that we discussed. So the first observation. Second observation is homothety center that H with ratio 2 sends the green points to the vertices. Because green points are the midpoints of this. The green point is the midpoint of AH. And this green point is the midpoint of BH. So when you multiply it by 2, it goes to B. When you multiply it by 2, it goes to C. This means that the circumcircle of the green points, which is what? The circumcircle of the green points is just the 9-point circle. Right? It passes through all of these. It goes to the circumcircle of the triangle. Sends the green points to the vertices. Therefore, it sends N to O. Because N is the circumcenter of the green points. O is the circumcenter of the vertices. Okay. So it's basically just this similarity. So HN, okay, in the figure it doesn't look like this, but HN is actually equal to NO. So this immediately shows that O is the midpoint of H. N is the midpoint of H. So together the conclusion is they are always situated like this. H, N, G, O. Let's call this 2x. This is x. This is 3x. Okay, 3xx and 3x in total. So 8g is 2 times GO. Alternative proof with another homothety. Let's call this 2 prime. Alternatively, do homothety from G. Consider homothety with ratio -2. Okay? So it will reflect and multiply by 2. Then the blue points go to the vertices. The blue points are the midpoints. Because BG is 2 times the distance from G to the midpoint. So if you reflect it and multiply by 2, it will go to the vertices. Alternatively, homothety centered at G. Centered at G with ratio -2. -2. Sends the blue points to the vertices. If it sends the blue points to the vertices, it sends N to O. Because N is the circumcenter of the blue points. And N to O. Which means N, G, O like this. X to X. Indeed. The same thing. So all of these are consistent. So if you just combine this with this, let me call this 3. So I have 3 proofs here, but 2 of them are enough, okay? The first one is an affine proof. The second and the third ones are homothety. So if you just use any 2 of these, this is concluded. We conclude this using any 2 of 1, 2, 3. Yeah, this shows that there are many proofs, okay? So this is the Euler line. So there are especially, let's say, especially HGO are important points. But in all these three arguments, somehow we use N. In one of them we do NHG, the other one we do NHO, and the third one we do NGO. So these are the ones that are easier to prove. But at the end, this proves that all 4 points are collinear, and the collinearity of HGO itself is an important conclusion. And if you focus on that part of the figure, it has important consequences. Well, let's say some consequences of this, or not consequence, but just some related configurations. So if you consider the midpoint, if you consider the just HGO, if you consider this part of the figure, H being the orthocenter, G, so these being altitudes. O is here, and G is here, okay, with this ratio. So this is the midpoint, and OM is perpendicular. So notice you have the ratio AG over GM is 2. HG over GO is 2 also. And indeed AH, OM are parallel. So this is really a similarity of ratio 2. One thing this shows is that AH equals 2 times OM. And if you therefore extend these, they will intersect at a point D, such that since AH is 2 times OM, this point will be, by similarity, AO will be OD, HM will be MD. So what does this tell you? AO equals OD means this is on the circumcircle. This is the opposite point. So it's a very important thing. D being the opposite point on the circumcircle, H and D are collinear and they are equal. So this is the statement. Let D be opposite A on the circumcircle. Then the midpoint of HD is the midpoint of BC. We don't need to put this in a box. So this is a very important figure as well. Okay. This by itself, this standard figure consisting of especially the orthocenter, the diametrically opposite point, and the midpoint. This part of the figure, this standard figure, and when you especially think of it in terms together with the centroid and the circumcenter, so that means together with the Euler line, this is a very important figure. Just this collinearity by itself, HMD, appears in several problems. This is something that must be known. We can, of course, prove this alternatively. So there are, since all these things are related to each other, there are countless number of proofs. You can start from any statement and prove the other statement. So this is a very, very much interconnected network of statements. From any statement, you basically conclude the other statement. The proofs that I give are just some of the proofs, okay? For example, here, you can already start thinking of another proof. Let me get you think. What does it mean that the midpoint of a segment is the same as midpoint of another segment? So two segments go through, well, share their midpoint. This I asked the same question to you yesterday, right? What's the meaning of this?
Yeah, this means that BOCD is a parallelogram.
BHDC.
B, yeah, I mean BHTC.
Yeah, BHCD. Yeah, BHCD. Sorry.
Yeah.
So, well, BHCD is a parallelogram. We can also prove this directly. Right? BH is perpendicular to AC, and CD is also perpendicular to AC, because AD is diameter. We can prove this alternatively by BH is perpendicular to AC and CD is perpendicular to AC. Therefore, BH is parallel to CD. Similarly, analogously by permutation symmetry, CH is parallel to BD. Notice another thing that this shows is that the length of BH is equal to length of CD. But length of BH is at the same time, by this argument, equal to 2 times the distance of O to the side length. If you call this K, if you call this midpoint K, BH is 2 times OK. But CD is also 2 times OK. You can see from similarity. So BH is equal to CD. This is another way to prove it. Or by observing BH equals 2OK equals CD. And similarly, CH equals BD. This also shows, when you have a quadrilateral with opposite sides having the same length, this also has to be a parallel. This is forced to be a parallelogram. These are all just alternative proofs for the same thing. This is an important figure, okay? Related to this subject, Euler line. All right. Now let me. So, do you have any question about this? Now, finally, I will discuss one more configuration. This configuration, I don't know if it has a name, but this is a standard one. So this I discussed it under the title of Euler line, but it's not part of it. So the next configuration I want to discuss is tangent circles. Namely, let's consider angle bisectors. Basically, there are 4 circles. The statement is this: there are 4 circles tangent to all sides. Exactly 4 circles. This is the statement. And let's try proving this. First, let's draw a picture and then try proving. So this is one such circle. So people, when they want to distinguish these circles, they try to describe their positions in terms of the interior and the exterior regions. Okay, in terms of these inequality properties. So they don't touch at the same point, of course. Saying that this is the in circle and this is the X circle on the opposite side to C, and there is an X circle on the opposite side to B, and there is an X circle on the opposite side of A. But they have the same properties. Algebraically speaking, they have the same properties. We don't have to distinguish. Okay? It is this figure. To prove this, let's locate the centers. You know, when you have a circle and two tangents to it coming from some vertex, if you just focus on this part, any circle and two tangents, then the two tangents are symmetric with respect to the diameter of the circle going through the point of intersection, right? If you draw this diameter, so if you look at the center of this and if you draw this diameter, there is symmetry. These two tangents are symmetric, which means this red line must be angle bisector. Okay. So to prove that these circles exist, you know, exactly such four circles exist, we need to find the centers, first of all, by drawing the angle bisectors. So what we really need to show is that the angle bisectors are concurrent. Okay. So similarly, this angle bisector must go through the center here. The center here. And this angle bisector, which is the external one. So this is, it's orthogonal to this at 90 degrees. These two must be on this angle bisector. And this one must be on this angle bisector. While these two must be on the angle bisector of C like this. And these two must be on the angle bisector of B like this. So this is the statement, and this figure always appears. How do we prove that this always appears? To simply show that here's what we really just showed. Choose any angle bisector from A and any angle bisector from B. You have two choices from A and two choices from B. You get intersection, so there are four choices for the intersection. This intersection must automatically be on the angle bisector for C. The reason is when it is on the angle bisector, by this construction, it has equal distance to the sides. Either this angle bisector or this angle bisector, both of them. The characterization is angle bisector is the set of points which are centers of circles that are tangent to AB and AC. So if I want to draw a circle, if I just ignore about BC, okay, I don't even think about the vertices B and C, I just think of the lines, AB and AC. I think of these two lines. And I'm trying to consider the circles that are tangent to this. So there are two possibilities. Circles can be tangent like here and here, or here and here. So the center of the circle is either on this angle bisector or this angle bisector. And conversely, when it is on the angle bisector, it has equal distance to both sides. So you can draw a circle that is tangent to both sides. Okay? So the proof is just this. For any point I, if two of AI, BI, CI are angle bisectors, By angle bisectors, I mean external or internal? External or internal. If two of them are angle bisectors, then the third one is automatically an angle bisector. You must have seen how this proof is really similar to our proof of the concurrence of radical axes, somehow. Alhamdulillah. Sorry about that. And the third one is automatically an angle bisector. So you can just take A and B. So if AI is an angle bisector, internal or external, BI is an angle bisector, external or internal, then CI must be an angle bisector. The reason is because a point on or because, let's say, because if AI is an angle bisector, then I has the same distance to AB and AC. So if AI and BI are both angle bisectors, so I has the same distance to AB and AC, and it has the same distance to AB and BC. So it has the same distance to all three of them. CI is also an angle bisector. So for this reason, you can choose any angle bisector from a vertex and any other angle bisector from the other vertex. 2 times 2, you get 4 intersections. Then when you join that when you join one of those 4 points to the other vertex, it must automatically be an angle bisector. So you don't get 2 times 2 times 2, 8. Remember, Kerem, you had made this comment before. You cannot just choose the third one arbitrarily, because then it will not go. So if I choose this external and this external, the third one automatically becomes internal. So there is some orientation reason for this. So there are these 4 points. This is an important configuration. We can call them I1, I2, I3, I4. And the connection of this figure. So this figure is much richer. It's not just this part. Okay. Let me draw it again without drawing the circles. Let me just draw the red part of it. The connection of this to what we previously saw is that these 4 points is an orthic system. And conversely, any orthic system has this structure. Welcome, Abdullah. Tangent circle centers form an orthic system. Orthic system. Conversely, any orthic system is such. You can think of this as an interesting another way to find an orthic system from a triangle. So far we have been discussing a triangle together with its orthocenter. These 4 points forming an orthic system. In this one, it is different. We formed the orthic system like this. Not from the vertices of the triangle, but from these 4 points. So and this is an obvious statement. These are the angle bisectors. This is because external bisector and internal bisector are orthogonal to each other. This is an orthic system. So what can we want to do with this orthic system? For example, we can consider, so what do I mean by conversely any orthic system as such? What do I mean by this statement? Do you understand this? What does this statement mean? So after this configuration, I will start solving problems, okay? By the way, I didn't solve the 3 problems that I gave you as homework yesterday because you have not solved them yet. So I still want to give you time to solve them. Today I will solve other problems. So, by the way, do you want to have any other lecture after this one? It is
Yeah, I think one more would be good.
one more would be good. Yeah, but the thing is, Friday, Saturday, and Sunday are, I guess, difficult for me. So the earliest we can have is Monday, which is 7th. You are traveling on Friday, right? Next Friday, inshallah.
Inshallah, yeah.
Inshallah. Okay. So I remember Tasim wanted to give you a few days off from before going to get rest in your mind. But let me know if you want to have another lecture on Monday, 7th. I can give you another lecture solving problems because I think this is the end of the configuration discussions because these are the most fundamental. Of course, there are more configurations like the notion of a Simidian, stuff like that. I mean, there's lots of stuff. Not too many, but what I already discussed with you together with this one is, I believe, 90% of the important triangle configurations. Okay, this is really 90% in terms of the configurations that we see in the IMO problems of level 1, 4, 2, 5. At this level of the problems, the standard configurations that we see, 90% of the standard configurations that we see are like this. So after discussing this configuration, I will solve problems for the rest of today, inshallah. And if I have another lecture with you, I will completely solve problems. So yeah, if it is good for all of you, we can have another lecture on Monday. Not tomorrow, but Monday. So in this one, what did I ask you? What do I mean when I say this? That conversely any orthic system is such. What do I mean is, take any orthic system, okay, the red points, then construct the intersections, these feet of altitudes. So when you start from the opposite, it works in the same way. If this is any orthic system, if you take these 3 points, then necessarily these altitudes are angle bisectors. They have to be angle bisectors. So this is something we could have observed yesterday. We didn't observe because of the other things, but yeah, when we talked about the orthic system, here we talked about an orthic system, for example. Here, these orange points, if you look at these orange points, construct a triangle of the orange points, the black points of the orthic system are intersections of angle bisectors for the orange triangle. Okay, so this line BC is an external angle bisector for this orange angle, and line AD is an internal angle bisector for this. Similarly, the line AB is an external angle bisector for this orange triangle. It's always like that. Maybe we should prove this. So the fact that these form an orthic system is clear, but conversely any orthic system is such because Let me slightly move the statement. For this, yeah, when you take any orthic system, let's try to prove this angle equality. I'll just take any orthic system, okay? And let's look at these orange points. Okay, can anyone prove this angle equality for me? That this angle is equal to this angle. It's just angle chasing.
Yeah, because
Yeah, let me give names to this. A, B, C, D, and these are K, L, M. Yeah. So MKD equals,
is equal to DKL,
yeah. How do you do the angle chasing?
because we have the quadrilateral ALKB is cyclic, because we have 90 and 90,
Yes.
and this and the same thing for the others, MLCB and AMKC,
Yeah.
and so we have angle BKM is equal to angle A, and angle LKC is equal to angle also A.
Yeah.
So they are equal, and we have
So
this
it's
is
90 minus
90.
A, 90 minus A.
Yeah,
Yeah. Or you can do it from these circles. So BMDK is also cyclic because this has diameter BD. So there are 6 interesting circles here with diameters. So since there are 6 segments, 4 choose 2 is 6, right? From A, B, C, D. With the circle with diameter AB goes through KL. Circle with diameter AC goes through MK. Circle with diameter BC goes through ML. Circle with diameter AD goes through ML. Circle with diameter BD goes through MK. Circle with diameter CD goes through LK. So all 6 of them. So you can use circles with diameter, uh, for example, yeah, BD and BA. If you use this, uh, this is not the only way, of course. I mean, if I want to move this point K, so I have to choose one of B or C and consider the circles. So for example, if I look at B, I should consider the circles BD and BA. So the circle with diameter BD, I mean BKDM. So this angle is moved to here. So now if I consider the circle with diameter BA, BKLA, this is moved to here. Okay. So or alternatively, what you said, Kerem. So this can be moved to, if you do it, if you move it from uh, yeah, circle with diameter AC, it is moved to here. And if you move it from circle with diameter AB, it is moved to here. So anyway, yeah, this is exactly what I mean. From any triangle, you construct an orthic system by the 4 centers of the tangent circles. And from any orthic system, you construct it like that. Okay, now the interesting thing is this. For an orthic system, the most interesting construction is that of the 9-point circle. So if I construct an orthic system from a triangle in this way, by the 4 points, 4 centers of the tangent circles, what is the 9-point circle? What is the 9-point circle of the orthic system of the red points?
it passes through the midpoints of the I1, I2, and I1, I3, and
Yeah, that's
I1,
true.
I4.
Those are the 6 points that you get, but also there are 3 more points that it passes through.
And the midpoints of I2, I3, I3,
No,
I4,
those are the 6 points, right? So if I call this I1, I2, I3, and I4, so 4 choose 2 is 6, as I said. So there
and
are
ABC.
the other 3 points are ABC. So the 9-point circle of this is just the circumcircle ABC. Okay.
Yes.
What is the 9-point circle of the ortic system? So when you draw this, when you look at the circumcircle, so it doesn't really add any other thing. It's just the circumcircle, the usual circumcircle. But when you consider the circumcircle from this point of view, together with this configuration. So when you just draw the circumcircle on top of this configuration and understand that it's the 9-point circle of this ortic system, it gives a lot of interesting information. What's the 9-point circle of the ortic system? I1, I2, I3, I4. This is the circumcircle. This is the circumcircle. Circle ABC. So let's draw this together. Draw these two things on top of each other. So external angle bisector, internal angle bisector, external angle bisector. Also external. This is internal and this is internal. So these are the 4 points that form an ortic system. So if I draw the circumcircle on top of this, so these additional 6 points are interesting midpoints. Okay. They are midpoints of, so let's call them, so these are I1, I2, I3, I4. So let's call this one X, for example. So X is the midpoint of I1, I2. But if you notice, X is also the midpoint of the arc BC, okay? Because this is an angle bisector. So this is a very interesting way to look at it like that. So this is the opposite point, Y. XY is, as you know, the diameter, because this is 90 degrees. Also, if you look at it as the 9-point circle, you can also see this. So in the circumcircle, XY is a diameter. X and Y are both midpoints of the arcs BC. So XY is the perpendicular bisector of BC. And X is the midpoint of I1, I2. And Y is the midpoint of I3, I4. So one interesting figure that appears here is when you see that X is the midpoint of I1, I2, X turns out to be the center of this circle with diameter I1, I2, passing through B1, passing through B and C. So you see that these are equal. Do you see this here? This happens for all of them. So for example, for Y, what are they? What are the things that are equal? Which distances are equal? So this has interesting connections. X, Y are the midpoints of arcs BC. Since they are midpoints, XB equals XC, but it also turns out to be equal to XI1 and XI2. So XB equals XC, but not only that, the same distance is equal to XI1 and XI2. And for Y, what equality you have?
Y I3 equal Y I4 equal Y I1.
Not YI1. You can have two things from I's and two things from the vertices. You must have the same format. You don't even have to look at the picture. You can just convert from here. Y is the midpoint of the arc BC, so automatically you have to put YB and YC. And then you can put the other things will be centers. Which centers will it be? Well, you will just look at the red line passing through Y. There is only one red line passing through it, which is I3 and I4. Okay, you can do it like this. If you understand how to do it quickly, you can do it for RNS as well. And you can do it for U and V. Let's quickly write them. So if you understand how this works, you should do it quickly. You should not even look at the picture. So R, you look at R. R is the midpoint of which arc? Well, which red line is it on? R is on the red line going through C. So it's in the midpoint of AB. So RA equals RB. And this red line goes through I1 and I4. S also goes through C. So S goes through C, I2, and I3. Since it goes through C, it is in the midpoint of AB. So I can write SA equals SB equals SI2, SI3. Right? Similarly, U. Who can do it for me, for you?
U I2 equal U I4, which equal to U A U and equal to UC.
Yeah, exactly. UA and UC equals to UI2 and UI4. And finally, for V, VA equals VC, which is equal to V. The remaining thing from here I can read VI1 and VI3. So all these points, so there is a lot of permutation symmetry here, okay? Between the points I1, I2, I3, I4, and between the points X, Y, RS, UV. As there is between A, B, C. So this is an important figure. Finally, I want to discuss one more interesting just conclusion of this with you. We can calculate the power of, let's just put O here for the sake of it. Power of any of these centers, these red centers, tangent circle centers, with respect to the circumcircle, easily because from this figure. For example, so powers of the tangent circle centers. They are all analogous. We can just do one of them. Tangent circle centers with respect to the circumcircle, with respect to the circumcircle. Okay, let's, for example, just consider this one. To prove the power, we will consider this segment, this chord, which passes through the midpoint, of the arc. And this Ix is equal to Xb. And so power, so let's call this gamma, okay, circle. I mean, okay, let's not give it a name because we are talking about this circle anyway. So power of I equals minus IA, Ix. Well, I put minus because of the picture. For the other external centers, it will not be minus. But if you really use, as I said, directed lengths and stuff, you will never have to worry about minus and plus. However, let's just do classical stuff. So Ix equals Xb. Or Xc, both of them the same. But the important thing here is, so let's give a name to this angle. Do you know that the chord length is sine of the angle times the diameter? Do you know this? This is diameter of the circle times sine alpha. Have you seen like this, something like this?
Yeah, we just
Yeah.
can extend XO and
Exactly. You simply extend, you just draw a diameter from X or B, one of them. Draw a diameter and connect it to the other one. You will have alpha and you will have 90 degrees. So diameter and alpha. So you will simply have this. So this is equal to minus 2R IA sine alpha. And IA sine alpha is just this length, which is equal to what? Which is equal to, this is the distance of the tangent circle center to all the sides are the same.
it's equal to, I think, the area over the semi.
Well, it's the radius. It's the radius of the
Yeah,
circle. Yeah.
and it's equal to the area of ABC over the
Oh yeah, you can say it that way, but I mean,
semi-broad.
there are other formulas for this. Yeah, that's true. But let's just give its name. That's what I mean. This is just the radius. So this is simply what this is. So the power is easily calculated like that. And for the other centers also, you have the same formula without the minus. So power of this is 2 times the radius of the circumcircle times radius of this circle, R4. So if you do it for this one, R1, for this R2, for this R3. So this is usually quoted as the distance. So from the power, you can calculate the distance, as you know. So IO squared minus R squared equals minus 2RR. So this is usually given as a formula for the distance between the centers. Because of the definition of power. And here I did the internal center. If you do any of the external centers, you put plus here and you change the radius little r to the to the radius of that circle. All right. So this has many interesting connections, as I said. This is just one figure coming from the tangent circle centers. The 4 points, it forms an orthic system, and any orthic system is as such. When you consider the circumcircle of ABC as the 9-point circle of this, you see this interesting connection, these length equalities. And from this you can even calculate some distances. So this is what I wanted to say. So let's now start solving problems. Do you have any questions about any of these configurations? All of these are really standard must-know configurations, okay? So let's start solving some problems. There is this classical problem that I solved many times in my trainings. I'm trying to look for it. Let me just try to remember it. The problem is in triangle ABC, you consider internal angle bisectors, and they intersect the sides at M and N, okay? And you draw the circumcircle, and the line MN intersects the circumcircle at XY. So show that this circumcircle of IXY, is twice the size of the green circle. Exactly. I mean, it means the diameter of this is twice the diameter of this. The radius of this is twice the radius of that. Show that circle IXY is twice the size of the circumcircle ABC. In this problem, the difficulties, as I said, difficult problems are the ones in which you need to discover points. So this is one such problem. In this problem, you need to discover some points. Okay. So let's start. Well, as I said earlier, as I emphasized earlier, I want to solve the problems out loud with you. So instead of everyone thinking by himself, any idea that comes to your mind, imagine you see this problem in the exam and you start thinking, you start brainstorming in the style, well, in whatever, say, thinking style you have, what is you're accustomed to, what you have learned from me or from other people, from other trainers or other sources that you've seen. Whatever way you want to think that you find helpful, but think instead of thinking internally, just think externally. Think out loud. Say your thoughts so that we can combine our thoughts and try to solve the problem quickly. Hopefully, we can pass
Mm,
the other problem.
maybe is it an easy problem to calculate the length xy and the angle yxi, because
Why I?
they are just about the triangle ABC, so maybe they are easy.
Maybe, but I don't think it is so easy because to calculate uh, because points x and y are defined in such a way that they are on the lines mn, on the line mn. The line mn is, say, not a very good line, so it's the intersection of the line mn with xy. So really, in order to get anything about the line xi or line yi, uh, then you need to have a lot more information about the point x. Maybe it might be possible to discover more information. Somehow, as you know, in geometry, lots of things are concurrent. They pass through the same point. So sometimes they define a point as the intersection of two things, but then other things also go through the same point. That's possible. You can discover other things that go through this point, so you can sort of maybe characterize what this point is. But before doing that, without doing that, just with this information, how can you get anything about the line xi? This is pretty much invisible and intractable. So this doesn't make it easy to calculate the angle yix. Similarly, the lines ya or xa, if you don't get anything about them, it makes it difficult to calculate the length xy. But other things that might possibly be easier to do is to discover other points on this circle, on the blue circle, in a way that will help you forget about the points x and y. You can use the information about x maybe to prove that some things are cyclic with yx. If some
What's
point
I in this circle?
I is some yes, so these are angle bisectors. Yeah. I is standard notation. So I is the center of a tangent circle. In this case, it's the internal tangent circle. But it doesn't matter. Instead of taking the internal tangent, so we can have alternative pictures for this, right? In the problem, it was given as internal tangent circle, internal tangent center, in center. But we know, because of our professional point of view, alternative pictures. These alternative pictures are not valid for the exam purposes, but they are helpful, as I said, for us to solve the problems. Sometimes they can be helpful. We can have an external, for example, we can have both of them external or external and internal. Although we have to wait, let's make it like this. Let's draw this external, for example. Let's draw this internal. So this is I. Somehow, yeah, this is point M. So you can have I here, then this would be M, and this would be N. So M would be the same thing in this case, because the same internal bisector. Okay, I just took the same internal bisector. M would be the same, but N would be different, the other point. Then you can still have, okay, let's still have the circumcircle, of course. And this green thing intersecting the circumcircle at X and Y. So in this case, again, we are talking about IXY. See, the picture looks kind of different, but it's really the same problem. So already what I said is kind of like a hint for you. Try to discover some points by some intersections in this figure. Okay? Look at some intersections and try to prove that something is cyclic with I, X, Y, something like that. Basically discover other points on the blue circle. And if they are better points, then it can help us prove this statement easily. We are trying to understand the blue circle at the end. Right? This is our target. Our target is to understand the blue circle. The blue circle is defined as the circle passing through I, X, Y, but if we can discover more points on the blue circle, then we can ignore X and Y. X and Y will be used only to discover these other points, which are better points. This is an insight. So this is the kind of approach that you have in some problems. And this is one of them. It's not easy to think, honestly, in this problem. It's not easy to think that you will discover other points on the blue circle. But maybe after, so if this was genuinely in the exam time, if after after working on this for a while, uh, if you after you can't do anything, you can come up with this idea maybe. Okay, guys, what are your thoughts? What kind of points you can discover on the blue line? For example, sorry, blue circle. For example, you can try to do it in the opposite way. You can get something, some of the other things intersect with the blue circle and try to understand that point. Try to understand another property of that point. Okay, when you have two properties about a point, that defines the point, right? When you have, something, some line and another line passing through it, that's the intersection, or some line or another circle, that's the intersection. So typically, to understand the point, to define a point means having two things passing through it. But to understand it further means having another thing, third thing, fourth thing passing through it. So here, when we say that we want to discover other points on the blue circle, we mean two other things, intersection of two other things being on the blue circle, right? So otherwise we can simply say that intersection of the blue circle with whatever line, it's automatically on the blue circle. This doesn't help us. But if we say intersection of such circle and such line defined from the triangle itself is on the blue circle, then this helps us. But to find it, maybe we can just take one thing from the triangle and intersect it with the blue circle, then try to discover something else about that point. If we can do it, then it can help us. This is a sort of backward thought. Is there anything interesting that you think that we can intersect with the blue circle? Certainly, it is not the circle because it's already the intersections are already x and y. Anything from the triangle that can be helpful, for their intersections with the blue circle. And obviously, we don't want to just intersect blue circle with an arbitrary line, because then we would get two intersections. It is better to get one intersection and try to understand it. Well, if one of the intersections, obviously since there's a circle, it necessarily has to have two intersections with anything. However, if one of the intersections is already known in the figure, then the second intersection would be easier to understand. You see, these are very general thoughts, not specific to this problem, but if you think like this, in terms of these general thoughts, it should help in the problem. So I want to choose something from the figure of the triangle, some line or some circle, and intersect it with the blue circle in such a way that already one of the intersections is there. Already one of the intersections is on the circle, which means it's already on the blue circle. And I want to look at the second intersection. Then I want to discover some properties about that. Well, what is already on the blue circle? Except x and y, which I don't want to have. There's only one point, right?
I.
Yeah. There is only one point I on the blue circle, so I should look at the things that pass through I. Okay? I should look at lines or circles somehow that pass through I, and I should intersect them with the blue circle and look at the second intersections to see if those second intersections are somehow good or not.
Maybe we consider the circumcircle of IBC. Is it useful? Because we know that its center is in the midpoint of arc BC.
For example, maybe. But there are even easier things. There are even easier things than this. You don't have to think of a circle. You can think of lines. But yeah, what's it?
The angle bisector of A.
Yeah. But what is even better than this? Okay, I understand both of the suggestions that you made are sort of self-symmetric suggestions, because in this problem there's permutation symmetry of B and C. So A is a special point, but we can change B and C. When we change B and C, M and N also change. However, we can do something, so some pair of things. It doesn't have to be just self-symmetric thing, right? We can. So it's not only AI that you can consider. Meaningfully. In some sense, it is better to consider, two things, two different things, pair of permutation symmetric things, because then you will have two intersections, and when you understand one of them, you automatically understand the other. What I mean, is it clear what I mean or not? Maybe not clear. Just think of lines or circles that go through I, and start with the simplest thing. Start with the simplest things without complicating. Which lines or circles that pass through I would give me the best information? If I already have some information about those lines or circles, then that is better. Then those would give me more information because I can study them. Already in the figure there are some lines passing through I with some information on them. Which lines passing through I have information on them in this figure? It is already drawn in the picture. It's already
The angle bisector.
what?
The angle bisectors.
Yeah, BI and CI. This is better than AI. You suggested the angle bisector AI, but BI and CI are better for two reasons. One thing is, if I understand one of them, if I understand the intersection of BI, I will automatically understand the intersection of CI. So I will get two good points, not just one. But if I understand the intersection of AI, that will be 1 point, right? So this is one reason it is better. And secondly, BI is already in the figure and passes through M. And this is something we can use, because in order to get information about the intersection, I will need to use X and Y. I will need to use X and Y, which are defined in terms of M and N. So I will need to use M and N. So it is good that my line also has some information about M and N, right? But if I draw AI, it's just an extra line. It doesn't have information about M or N. So it's good that our information pieces are aligned so we can possibly get something. This is the insight. This is a difficult problem, by the way. This is more than IMO14 level. At least 5 or something. So can you get something about this point? The second intersection of BI with the blue circle. Do you find any other information? So let's call this, for example, R. Let's call this R. So do we have any information about R? From the fact that R is on this circle, so Rx, Iy are cyclic. And what we know is IR is the angle bisector. It passes through M. This is the information that we have. IR is the angle bisector. It passes through M. What is M? M is just by definition this point, but Since we want to use x and y as well, we know we have to use that xy passes through M. So it is important that IR passes through M. So we need to use that these are cyclic to discover some information about R. Any idea about this?
Maybe we consider the powerful point of M.
Yeah, this is a good idea. Absolutely. So MR times MI equals MX times MY. So this is why is this good? Because it effectively gives the distance MR in terms of the distance MI and MX and MY. But of course, now you might say whether we know these distances, but what is even better is MX times MY. We have MX times MY.
Yeah, it's equal to AM times AC.
Yeah. So this kind of saves us uh, from X and Y.
Yeah.
Because MA times MC should be easier
Yeah,
uh,
we can calculate, yeah.
to calculate. So the equality that we have now to find the point R is MR times MI equals MA times MC. So, okay, this can help us maybe do some calculations from the triangle information. We can calculate the pieces, the length of MA, MC, and MI to find the MR, maybe to get some information. But okay, this is too much calculation. It is possible, but what would be perhaps a better way to progress? But we have already discovered an important thing. We have, I think, kind of saved ourselves from X and Y if we can study this equality. What does this equality mean geometrically to further progress? So this is the first discovery.
Maybe we could get some similarity.
Yeah. By the way, you directly have power equality. So you should think about interpreting this geometrically as power equality. You know, the converse of the power equality is also true.
Yeah, so they are cyclic.
Yeah. So
Oh, I go around Earth.
yeah. So this immediately gives that R IAC is cyclic. So this is exactly the kind of thing that I am saying. R passes through. You see, we have discovered something else that passes through R. We have discovered that this circle passes through R. So R is the intersection of the internal bisector with this orange circle. Now you can know what point R is.
We can calculate CAR. It's just equal to the sum of B over 2 plus C over 2.
Yeah.
And it's equal to 180 minus A over 2. So it must be the external angle bisector of AR is the external angle bisector of A. So it's the X center.
Yeah, because this is the figure that we have, right? We already know that the internal bisector and the external bisector, sorry, internal center and the external center on the same bisector are cyclic together with the other two vertices. that we know from here. This one. So internal and external. It doesn't have to be internal and external. So two centers that are on the same line. So when you just join any of these two centers, it passes through some vertex, and the other two vertices see this with 90 degrees. So they are on a circle together. So this shows that this must be the external center. Yeah. Since R is the intersection of the circle IAC and the line IB, this intersection is automatically the other center. R must be a tangent circle center, external one. For example, when you do it on the alternative picture, R becomes this. Okay? In the alternative picture, R becomes this, and this time it is the internal center. And you can do the same calculations. MR times MI equals MX times MY. This is MA times MC. This time, this is the orange circle. Again, IAC circle with the internal bisector. So that's a center. Now the other intersection also automatically we understand it. This one. We should not just think of this as alone. This is the other internal center. So other tangent center. So this SR is necessarily an angle bisector. It passes through A, and it's the angle bisector. You see, this has really almost solved the problem. In this case, S is this point. We do the same calculation. We do power of n, ns times ni equals ny times nx, which is nb times na. So a, b, s, I are cyclic. So here you do with n, ni, ns equals ny, nx, which is equal to na, nb. So si, ib, SAIB are cyclic, so S is the external center. So here you do the same thing. SIAB are cyclic. Of course, in the problem you will not draw this picture, but sometimes in the problem they give this kind of picture to just make it more difficult. Okay. So in the problem they always tell you whether you should take the internal angle bisector or external angle bisector. They give enough information about inequalities to specify the picture for you. However, usually that's not important. For example, they could have given it like this in the problem as well. Then you could have thought of drawing this picture. Whichever one is easier for you. You can look at that. Okay. So have you completed the solution then? Or still more ideas? So consequently, let circle IXY is the circle IRS, where R and S are the tangent circle centers, on the other bisector. Other bisector of A. Other angle bisector of A. By other, I mean not AI, right? So this requires us to draw a different picture because now we have completely saved ourselves from X and Y. Because these points are much easier to know, and this even has saved us from M and N. Now we are saved from X, Y, M, N. Because R and S are directly defined. There is this external bisector and these internal bisectors. This is I. RS. This is I. This is external bisector. Okay. The problem is about the circle IRS. What do you think about this circle? What? So this is a general thing now. This is a general thing. This is a standard configuration now, right? This is not even a problem anymore. This is a standard configuration. By itself an amazing thing. So we should go back to the previous page and say this as a standard configuration. That this circle is 2 times the circumcircle. Really, is this true as a standard configuration? If you look at this picture, which circle is it? I1, I3, I4, or I1, I2, I3, or I1, I3, I2, or I3, I2, I3, I4? All of them. There cannot be any difference. This is an amazing thing. All 4 circles. Are they of equal size? So, what do you think? Is this true in a general orthic system? In an orthic system, ABC, ABD, ACD, BCD, these 4 circles, are they of equal size? Because if the problem is true, it has to be true like this. If the problem is true, it's a general information.
Maybe we have, do we have some similarity here of triangles? Like SIR and BIC.
No, I think nothing special can happen in the problem because there is no information. In the
But
problem, there is
actually,
no information. So if this is true, it is true in general.
I know, but
So we have to go to the general thing, okay? To understand it better, we have to go to the general thing. In an orthic system, all these 4 circles are of equal size. Okay? Can we prove this? In general? But in the problem, it asks us to prove that any of these circles is 2 times this one. So about an orthic, if we formulate it in an orthic system, what does it mean? So it says these circles is 2 times the circle ABC, which means for an orthic system, the circle ABC, BCD, those circles are 2 times the circle MKL, which is the 9-point circle. Okay? So it tells us that the 9-point circle is half of these circles. BCD, ACD, ABD, ABC. So this is general information that I must add here. I must add the information here. Because this is general information. How can we prove this? Note. In an orthic system. So notice, even when we solve a problem, we find general information to discuss in the problem. Right? It never ends. In an orthic system. In an orthic system, the circles these 4 circles. Unfortunately, I cannot write. I don't know. A, B, C. Sorry, I will. My tablet pen, sorry, tablet marker doesn't write well. Maybe I should change the tip. Anyway, I cannot do it right now. Circles A, B, C, A, B, D. Oh, this doesn't write. Yeah, this doesn't write at all. Are of equal size. Okay, this is the note. All right, sorry for the interruption and the confusion. All right, in an orthic system, these 4 circles have equal size. And there's an important fact. And what does it mean? For example, let's look at this figure or this one. Forget about the midpoints and stuff. Just look at A, B, C, D. Equal size doesn't just mean equal size. Okay, it's something very important, because if you look at A, B, C and B, C, D, for example, B and C are the common points. And passing through these 2 common points, 2 circles are equal size, which means they must be symmetric with respect to BC. The circles ABC and BCD are symmetric with respect to BC. Similarly, any 2 such circles, so circles ABC and ABD, they must be symmetric with respect to AB. When you choose any 2 of these circles, so there are 6 choices that you can make, they are symmetric with respect to one of these 2 segments. So for example, you want to look at AH, so ABH and AHC. They are symmetric with respect to AH. And you can prove this easily because this angle ABH is equal to the angle ACH. Right? The proof is this. It's simply this. Since this angle is equal to this angle, but from the opposite sides. So the same segment, AH, is seen by equal angles from the opposite sides. So B and C are not on the same circle with respect to AH, but they are on symmetric circles. So ABH and ACH are symmetric with respect to AH. Similarly, BHC and AHC, BHC and ABC are symmetric with respect to BC. So think about this as such, okay? Any two of the circles is symmetric with respect to their with respect to their radical axis. Radical axis is the one. Obviously, the radical axis of ABC and BCD is, for example, BC, because their intersections are there. Think about it like this. So this is easy to prove. Moreover, these circles, since they are of equal size, the 9-point circle is half of them. Okay, the 9-point circle this circle is half the size. Half the size of the circles ABD. These equal circles, right? ABD, ABC, ACD, BCD. Why? How can you prove this? How can you prove this? It should not be difficult. Just focus on any of these triangles and look at the midpoints. Look at ABD. What are the midpoints? Red, blue, green. If you focus on any of these triangles, you will see the red points, the midpoints, red, blue, green. Okay. So they are on the 9-point circle. The midpoints form a triangle which is half of the triangle. So this red, blue, green, this triangle is half of the triangle ABD. Obviously, circumcircle will also be half. This is what we did with homothety on the next page. So this is what we did with homothety here. When we did homothety of ratio 2, the 9-point circle goes to the circumcircle. So 9-point circle must be half of the circumcircle. Here we did homothety with ratio -2. So we reflected and multiplied by 2. Again, the same thing. 9-point circle is half of the circumcircle. This is what we already saw on the previous page, right? 9-point circle is half the size of the circumcircle. By the way, so this comes from the homothety arguments, but we also saw, well, this comes from the homothety arguments, but we also saw this on the previous page, right? This is exactly what we saw here. and it's the circumcircle of any of these 4 triangles. So just in a triangle configuration setting, the fact that ABC and BHC are symmetric is already good information. This somehow appears as such. The point that is symmetric to H, reflection of H on BC is on the circumcircle of ABC. Let's also put this on our configurations here. For example, yeah, this is something else that we can put. We can extend this. And since this is the diameter, AD, this must be 90 degrees. And since this is also 90 degrees, this is parallel. Okay? So these are equal. So this point is the reflection of H in the side BC. So this is why circumcircle ABC is symmetric to circumcircle BHC. They are symmetric, they are of equal size. This is another way to see it. So when it comes to tangent point circles, tangent point centers, of course, taking any 2 of them, I1, I2, I3, this circle is twice as big as the circumcircle. So in the problem, this is what is asked. This circle is twice as big as ABC. Do you agree? Well, this is why I stopped here and tried to do it generally, because if this is true at this stage for the problem, since there is no special information about the triangle, it must be true in general. This is how I discovered it. So I went back to the original thing. So I said it must be true for all these 4 circles. And there is again no special thing for these 4 points. It's just any orthic system. So it must be true in an orthic system in general. So this is why I went to even the previous page. So I discovered it there. I discovered important information about an orthic system, that these 4 circles are of equal size. They are symmetric with respect to the radical axes. They have the same size, and this 9-point circle is half of them in an orthic system. So it also holds for the tangent point circles in general, tangent point centers. So it also holds for this problem in particular. IRS is twice the size of ABC. Standard is a standard fact. Now this is standard fact. Because we can say because ABC is the 9-point circle of IRS. This is the reason. In fact, A, B, and C are the feet of the altitudes of IRS. Because IA is perpendicular to RS, SB is perpendicular to IR, and RC is perpendicular to IS. These are the feet of the altitudes. So this is the 9-point circle. This is the 9-point circle of the triangle IRS. So it is half of the circumcircle of IRS. All right. So I think we can finish today. Do you have any other comments? So the 3 problems that I sent to you are very nice problems. They are not as difficult as this one, because you don't really need to discover such extra points. So you can solve them, and you have 3 days now. So if we have another lecture on Monday, we will inshallah dedicate it fully to solving problems. And by that time, I want you to solve these 3 homework problems. And when you solve them, as soon as you solve them, send them to me on WhatsApp so that I can know who solved which problem. I need feedback for this, okay? If you solve them, for example, if most of you solve most of those problems, I can solve them quickly in the beginning of the next lecture and solve some additional problems. Otherwise, if you don't solve them, I will spend more time on those problems in the next lecture. On Monday, inshallah. Okay, anything you want to say? Any comments? All right, so if you have any questions, you can also text me on WhatsApp. Abdullah, I think I don't have your number. I have everyone else's number because they sent me some solutions before, but I don't have your number. So
Okay. I will send you.
yeah, some message. All right. All right. See you next time, inshallah.